So we've seen in a previous unit of study what happens when you combine capacitors and resistors together in a circuit. So let's say we have a switch and a resistor and a capacitor all in series with a battery. We'll say the battery has an idealized voltage that we symbolize with the symbol for EMF. So there's our resistor, there's our capacitor. Without going through the full derivation, if we wanted to express the amount of charge on the capacitor as a function of time, we get Q equals Q max times 1 minus e to the negative t over tau, where we called tau the time constant. And the time constant is just equal to the product of resistance and capacitance. The idea here is with greater resistance, you'd have a smaller amount of current flowing, and if less current flows to the capacitor, it should take more time to charge up. The other idea is if the capacitance is larger, then it's going to take more time to fill up because it's a bigger object to fill. So the time constant is directly proportional to both the resistance and the capacitance. So it turns out that a second is what you get when you multiply an ohm times a farad, right? There's no distinction between a second and an ohm farad dimensionally. Well, in this unit and in this video, we're going to see what happens when we combine inductors and resistors together. So let's draw a similar circuit. There's a battery with an idealized voltage, and it's in series with a switch, a resistor, and an inductor. Well, let's just apply Kirchhoff's loop rule. And see what we get. We'll start from X marks the spot, work our way around the circuit, and say what is Kirchhoff's loop rule. The overall change in voltage around any loop should be equal to 0. So we have E minus IR minus L di dt is equal to 0. We'll call that step 1 of our derivation. So now it's just some algebra and rearranging from here. It looks like negative L di dt is equal to, let me express this another way. Instead of IR, I'll call it RI. So this is equal to RI minus EMF. And then let's cross multiply. Di divided by Ri minus EMF is equal to negative 1 over L dt. Let me multiply both sides of the equation by R. All right, that gets us to step 4. It looks like di over I minus E over R is equal to negative R over L dt. So far, so good. Whatever we do to one side of the equation, we'll do to the other. So let's take the integral of both sides of the equation. So let's see. We'll say time t equals 0 is the moment that you drop the switch. So we're going to integrate from 0 up until, well, we'll just integrate up until some random amount of time. Okay, well, at t equals 0, initially, the current is equal to 0. And when you drop the switch, you would think we could just apply Ohm's law. After all, an inductor is just bare wire that's been coiled up, and bare wire doesn't add any resistance, ideally, to the circuit. So it seems like the amount of current that flows once we drop the switch should just be the voltage of the battery divided by the resistance. However, if you think of inductance as a form of electrical inertia, then the current can't suddenly jump up to this value. It has to gradually grow from 0 up to that value. In any case, at time t equals 0, the current starts out at 0 and eventually grows to some current I. Well, negative R over L, that's all a constant. So on the right side of the equation, in step 5, just say we get negative r over L times the integral of dt from 0 to t. But of course, that's just going to give us t. Okay, what do we have on the left side of the equation? It looks like our solution is going to be natural log, right? I think it's going to be the natural log of I minus e over r, and then we have to evaluate that from 0 to I. So step 6 looks something like this. The natural log of I minus e over r divided by negative e over r, so we've applied our limits of integration, is equal to negative r over L times t. Whatever we do to one side of the equation, we do to the other. So I'm going to raise e to whatever expressed on both sides of the equation. So in step 7, we get I minus e over r divided by negative e over r is equal to e to the negative r over lt. And then we cross multiply on both sides of the equation. We're going to multiply by negative e over r. So it cancels out on this side of the equation. And so we get to step 8, I minus e over r is equal to negative EMF over r times e to the negative r over lt. So now we just have to add EMF over r to both sides of the equation. And we land on a final expression for current as a function of time. The current is equal to the battery EMF divided by resistance times 1 minus e to the negative r over L times t. This should all seem familiar. This is very much like the derivation we had for the RC circuit. It's just that in the RC circuit, we found that the charge on the capacitor gradually grows with time. So if time t equals 0 is the moment you drop the switch, then the charge doesn't instantly build up on the capacitor. It takes time for the charge to build up. And if we were to make a graph of charge versus time, an equation like this graphs out as if the charge is approaching an asymptotic maximum value. And that maximum value is just what? Capital Q, call that Q max, is equal to the battery voltage multiplied by the capacitance. So it's a similar expression here. What's gradually increasing in time from the moment the switch is thrown is not an amount of charge, it's an amount of current that's gradually growing. The current that passes through the resistor, and therefore passes through the inductor since they're in series, goes from an initial value of 0 up to some maximum value, and a graph looks something like this. Current versus time, well, if we say it's an ideal inductor, if the wire that's used to wind it has very low resistivity, then there's no resistance from the inductor. The resistance is all in the resistor. By the way, in the ideal world, winding a bunch of coils of wire has its own internal resistance, but we'll deal with that later. For now, we'll imagine that there's such thing as an ideal inductor that has no resistance to it. So the maximum amount of current we get, call it I max, should just be equal to, according to Ohm's law, the battery EMF divided by resistance. But it doesn't get there in an instant. At time t equals 0, we drop the switch, and the current gradually asymptotically grows to the maximum value. So we can mark out a special spot on here. We'll say at this point, the time it takes to reach 63% of the maximum current is what we call the time constant tau, and that time constant tau is equal to resistance divided by inductance. So, oh, I'm sorry. I've got that backwards. The time constant is equal to the inductance divided by the resistance. as resistance goes up, then the maximum current would be a smaller value, right? The graph would look something more like this. And so if the current doesn't have to grow to as large of a value, it should take less time to reach 63% of the max value. So it makes sense that as resistance goes up, the time constant goes down. However, as the inductance goes up, the time constant also goes up. Inductance is electrical inertia. So with a greater inductance, there's a larger back EMF that competes with the external voltage source to try to fight with the growth in current that tries to limit the value of not I, but limit the value of di dt. So as inductance goes up, tau goes up. As resistance goes up, tau goes down. And so there's our expression for time constant. So if we want to, we can simplify this expression for the current through an LR circuit. Instead of saying I equals EMF over resistance times 1 minus E to the negative R over LT, we can say that the current equals the maximum current times 1 minus E to the negative T over tau. So that's a general equation for the way in which current gradually grows in a circuit that has any amount of inductance.